All right, welcome back everybody to the Environmental Economics series. This is episode 5, and we're going to talk a little about discount rates. Last time we were talking about survey techniques and kind of where surveys can fall through the cracks in valuing ecosystem services. So today we're going to talk about kind of a continuation of that topic, but how discount rates affect how we think about environmental decision making. So first of all, what is a discount rate? A discount rate is kind of like an interest rate, but not exactly. You can think of it as the time value of money, or the time preference people have for a benefit today instead of tomorrow, or a cost today instead of a cost tomorrow. And its closest approximation is probably what you'd call like general rate of return in the economy, not strictly like an interest rate on a mortgage or something like that. But discount rates go up and down according to different things. How much capital is available in the economy? More capital, lower discount rate because there's a higher supply of capital to loan out. People's lifespan, longer discount rate because there's a higher chance you'll live to see your investment pay off. So if you lived in like 1200s Italy, probably have a lot higher discount rate. Probably won't make an investment that's only going to make 2 or 3%, that you're going to have to live 50, 60 years to see pay off because you probably won't live that long. And then also changes in the market, kind of fluctuations, and changes in people's time preference. So that's basically what a discount rate is. And the idea behind it is that a benefit today is worth more than a benefit tomorrow. This is universally true with money, right? It's the reason that if you loan money to somebody or somebody loans money to you, there's an interest rate. It's an expression of time preference. That a benefit now, if I give you $1 now, that's worth like $1.03 next year or whatever the amount is. That's an expression of time preference or the discount rate. So it's also a way to measure maximization of utility over time periods. It says, if there's a difference in what a benefit or cost is today versus in the future because of discounting, that implies that we shouldn't be thinking of everything as just a present decision, but how it has impacts over time. So, let's think about this. Are there things that you don't think you should discount into the future? I'll give you just a second to think about this. So the answer is probably yes. So there are some things that have more or less an infinite value, right? Like clean air or breathable air. What would you be willing to pay for breathable air? The answer is whatever you have. And as a planet, what would we be willing to pay for it? The answer is whatever we have, because it's an issue of staying alive or not. So the whole joke is that if you apply the discount rate to everything, then the end of the world in 500 years isn't really a cost you should take into account because it's discounted 500 years into the future, and by then it just looks like a really small cost. You can get around that by making the cost infinity because infinity divided by anything is still infinity. Anyway, so on a practical level, let's look at why this is relevant for decision making, both from the public trade-off, kind of marginal social cost and social benefit that we've been looking at, and from a private actor standpoint in the environmental context. So example 1 is a dam. So let's imagine that we're thinking about the decision making that went into constructing Hoover Dam here just east of Las Vegas back in the 30s, or Grand Coulee Dam up on the Columbia River in Washington. And so what is a dam like in terms of what it does over time? Well, what happens is first, when you build a dam, I'm just going to erase this for some extra space since we already went over the general concept and talked through this. When you first build a dam, you have a massive input cost where you have to pay for the materials, you have to pay for the labor, you have to do all the planning, get all the permits. It's just an immense startup cost to build a dam. So that's represented here by the fact that at t equals 0, or the 0th year at the very start of the project, we have a negative 100 revenue. Okay, but then after that, the dam starts producing electricity. And that electricity gets sold on an open market, and you start recouping some of your investment. And this is true both from the point of view of the private actor that built the dam and from society's point of view. So there are other costs to building a dam and other benefits, and we'll talk about those in a minute, kind of looping back to our externality episode. But for now, let's just think about it as startup costs and electricity revenue. So let's say in this hypothetical example that the dam only lasts 6 years, because I don't want to do, really complicated math going out to like 50 years or 100 years, on an episode like this. So obviously it's a simplified one, but let's assume it's going to produce electricity for 6 years. And what it'll produce is, at current market rates, $20 worth of electricity for each of those years. Okay, so if we don't take into account the discount rate, in other words, if we have a discount rate of 0, then 6 years of $20 revenue is $120, which exceeds our startup cost of $100. So we have negative $100 startup cost, but plus $120 in revenue. Oh, okay. So, then it's worth it, because total benefit or revenue minus total cost is positive. It's positive 20. So the project makes money over time. It pays for itself. So then this would say, yeah, go ahead and build it. But, what happens if we introduce a discount rate of, say, 8%? Now what happens is, instead of the equation looking like this, where it's really simple, negative 100 plus 20 plus 20, 6 times, right, because there are 6 years, now it looks like this. The negative 100 plus 20 over 1.08 to the first power. So we're dividing by a number bigger than 1, so this will get smaller. Plus, and the 0.08 is because our discount rate, remember, is 8%. So we take that 0.08 or 8% discount rate, we add it to 1. So we get that 1.08. Plus, in year number 2, 20 over 1.08 squared now, because you take it to the power of the number of years. Plus 20 over 1.08 to the third power, dot, 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 and then our last one is 20 over 1.08 to the sixth power. And this is accounting for that revenue in the future should be discounted by a rate of return, or the opportunity cost on it. Okay, so now what happens is, the revenue next year is $20, but in real terms, or in present value terms, it's only $18.50. I rounded all these to the nearest 10 cents. And then in year 2, we divide by a bigger denominator, so of course the overall thing gets smaller, right? And then now if you add all these together, they're not 120, they're 92.4. This plus this plus this plus this plus this, that's 92.4. So now we do the same thing we did up here. Is total benefit still greater than total cost? No, because you had to invest 100 at the start, but now you didn't even make 100 back. You made 92.4. So over those 6 years, the project does not pay for itself. It has revenue of negative 7.6, and now the inequality flips, where in the first scenario up here, where we didn't do discounting, total benefit exceeded total cost, and therefore you would want to build it. But now we integrate discounting, we see that total cost exceeds total benefit, and we would not want to. And so if you have, and of course a dam is not the only example, but if you're looking at some sort of environmental project or alteration where it's going to produce revenue in the long term, but it requires a really big startup cost at the beginning, then you want a lower discount rate for it to work. And if you're in a high interest rate environment where there's a high discount rate, it's not going to work, and it is not worth it. So it's very critical that anytime a local government or a state government or an agency, or even just you as a citizen are looking at a cost-benefit analysis, number one, it has a discount rate, and number two, it's got an appropriate discount rate. Now, if I were the dam company and I was trying to convince the state government or the local government, yeah, this project is worthwhile, do you think I would want to use a high or low discount rate? Really, really low, right? Like I'd put in something ridiculous like 1 or 2%, and then it'll look like this project is still net positive over the period. So, yeah, got to watch out for this. Now, the second example we're going to look at is just the opposite, where at the beginning you reap a benefit, but then over time there are costs. Okay? So let's think about logging. And logging is kind of like the opposite of dam building. So let's say we have, again, a Douglas fir forest in Oregon, and we go through and clear cut. You immediately recognize revenue from all of the timber you cut down and sell. But then you probably have to replant, and even if you don't, over the next years, there's going to be some cost in lost recreation value, lost carbon sequestration value, increase in erosion and sedimentation downstream and stuff like that. And so those costs will accrue over time until you can harvest again. And again, we're going out to 7 years. Obviously, it's not realistic. A realistic thing would be to go out, depending on the tree species, probably between like 15 and up to 100 years, depending on the climate and how fast the trees are growing and what the species is. So, but let's assume we have a timber rotation of 7 years. So at time equals 0, we cut the forest and we earn revenue of 100. But then, in each subsequent year, when the forest isn't regrown, we have a cost of 15, so negative 15. So let's do this. Without the discount rate, which is to say discount rate equals 0, same difference, is this worthwhile or not? And the answer is no, because we have an initial revenue of 100, but then this negative 15 times 7 is negative 105. So overall, it looks like total costs exceed total benefits at a discount rate of 0, so we would not go through, we would not log this forest if we're assuming this is a public forest where there's kind of a public decision-making process about it. Now let's apply a 10% discount rate. So all of a sudden the math is going to change again, where instead of just doing simple 100 minus 15 minus 15 minus 15, now we're doing 100 minus 15 over 1.10, because our discount rate is 0.1, so we add that to 1 to the first power, minus 15 over 1.10 squared, etc., all the way up to the last term in the sequence, 1.10 to the sixth power. Okay, and when you do this, the cost for year 1 shrinks from negative 15 to negative 13.6, negative 12.4, negative 11. The costs are getting smaller because the further out in the future you go, the more discounted that cost is, because it's further out in the future. So by the time we get to the end, the cost is roughly cut in half for year 7. And the total cost, when you add all these up, is no longer negative 105, it's negative 73. So now, it looks worth it, because if the revenue is 100, and the cost is only 73, we have positive 27 is total benefits minus total costs. So total benefits exceed total costs, and we go through with it, all else held equal. And so if you're in the opposite position as the dam, you're in a position where you're considering some decision that would get a benefit now, but then incur cost over a long time period. Then you want the discount rate to be higher, because it makes the costs that are out in the future look smaller. And if the discount rate is really low, the costs that are out in the future don't change. They don't get smaller at all. So, from this, we can say that as a general rule, the higher the discount rate, which is symbolized by I, the smaller future benefits and costs look. So think about a car mirror. Like as a kid, you're riding in your parents' car and you saw that label, objects in the mirror are closer than they appear. Well, with a discount rate, if you're using too high a discount rate, then objects in the future are bigger than they appear. And if you're using too small a discount rate, objects in the future are smaller than they actually appear. So we can say that projects with a benefit right now and then a cost that's spread over time, they benefit from a higher discount rate because those costs in the future are discounted. They become smaller. And the higher the discount rate, the smaller they get. And then on the other hand, projects with a cost now, like the dam, and then a benefit that accrues over time, those benefit from a lower discount rate. And a lower discount rate obviously means that those benefits in the future don't shrink as much when you apply the discounting. Okay, now we did these two examples, the dam and the logging, where we were at 6 and 7 years. Obviously, a dam lasts way longer than that. Logging lasts way longer than that. You would need like series notation to actually solve a problem that long, or to do it in Excel or something, but we're obviously not going to go through that here. And there are some projects that have an initial investment and then a really long useful life and then an ending cost. Dam is actually an example of one, because at some point the infrastructure will start to break down and you'll have to remove the dam. And so that'll be a cost. It might be 100 years in the future or something like that. But it actually has a beginning cost and then a useful stream of benefits and then a disposal cost at the end. And for those, what you'll find is that there's not like a point where above this discount rate the project works and below it doesn't. There's a range where it works. So it'll be like an inequality where the interest rate or the discount rate has to be greater than 3 and less than 5. Because if it's above 5, then the stream of benefits gets discounted so steeply that the initial investment doesn't look worth it. But if it's below 3, that ending cost at the end of its useful life is not discounted enough for the whole thing to be positive, because you have a really big negative at the end. So you'll actually get an interval like this. So practically, what's the point of all this is that you have to take the time value of money and the time value of cost and benefits into account. That almost every public policy proposal or proposal to a town or state council or whatever for a major development will have a discount rate built in, and you need to know what that means and what the incentives of the various players are in forming that discount rate and whether it's reasonable or not when you're reading through there and deciding, whether you're the policymaker or just someone who lives in that town or whatever. Is this skewing their math? What happens if I move the discount rate up 1% or down 1%? All of a sudden, does this look like a horrible idea if interest rates just move around by a couple of percent? So it's kind of a useful concept to know about. And then also, we said at the beginning, this dam, we kind of just accounted for the fictional dam startup cost and then the value of the electricity generation. But there are external costs to building a dam. Like when you build a dam, unless you put in some special equipment, right, it's like the fish can't migrate upstream, so you lose fishing opportunities upstream. You also actually get, ironically, because dams are put in as sort of a clean power source, but if the water slows down behind the dam, say you've got a cold, rushing Appalachian stream, then you dam it up. Well, cold water holds a lot of CO2, and it holds a lot of gases. So if all of a sudden you get a lake that's really warm, number one, obviously it'll kill some native fauna that live in that river, but the water temperature will go up and it won't be able to hold on to as much gas. And then you'll get algae growth. And algae, when it dies and decomposes, again, puts off carbon. So ironically, you might actually get an increase in CO2 emissions from putting up a dam, in the irony of all ironies, but that doesn't happen every time. So these are external costs. And then the other point here is, obviously, for these tables or this sigma series notation to work, and for you to come to an accurate decision, or your town or your state or whatever, regarding a development, the costs and the revenues have to reflect reality, and they have to reflect costs that there's not necessarily a tradable market for. Like, what's the value of fishing in this river without there being a big dam there? So again, that links back to the episode we had on externalities and doing surveys to kind of capture those values when you're thinking about making these decisions. So I hope that you found it informative and that y'all are enjoying this series. Thanks for hanging along, and check back in probably next weekend for episode number 6. Happy herping, everyone.